Ya, Assalamualaikum warahmatullahi wabarakatuh. Alright, for today's lecture, we are going to look into structural steel beam design according to Eurocode 2. For the course outcome, it will cover on CO1, CO2, and lies with the program outcome PO2, PO3. The learning outcomes at the end of this topic, the student should be able to describe the behavior of restraint beams, and then you need to analyze and design restraint beam. So what is steel beam? So the primary function of beam is to transfer the vertical load to the adjacent structure element, normally column, so that the load can continue the path through the structure to the foundation. So the uses of beam is actually to support floors and columns, and also to carry roof sheeting as purlin and side cladding as sheeting rails. Beams may be a uniform section or non-uniform section. Sometimes we strengthen a beam at the region where the maximum moment occurs by adding cover plates or hunches. Okay, there are several types of steel beam. The most commonly steel beam is we are using hot roll section, that is I section, and also hollow section, and it could be cold form section. And the beam is also can be fabricated by welding. So for this one, the I section is welded, the box section, or we can also have standard I beam. Then we cut it so that we have tapered beam. We also have castellated beam and also composite beam. So depending on the structure that we are going to build and what kind of beam that we are going to use. Okay, for our design, so basically we are going to look into the design of I-beam section. What are the failures in steel beams? The main failures in steel beam is due to buckling and also corrosion. So buckling can be local buckling at the flange or at the web of the section. Okay, so let's look into action on steel beam. There's not much difference between the loading on steel beam and the loading for concrete beam. So basically they are similar. So the type of beam action, we have concentrated action from secondary beams and also some columns. And also we have distributed action that comes from the safe weight and also floor slab. Okay, so this is the example of steel structure that we have here. It is a floor slab and some column on top of the beam. For concrete, normally we don't have column on top of beam, but for steel beam, we are going to have, maybe we are going to put a column on our beam. So the column will act as axial load or point load to the beam. And also we have secondary beam, which is beam the other section, subjected to the main beam. So it will apply a point load to the main beam. So basically in the analysis, you have to transfer all the elements that we have here into free body diagram, and then you need to calculate what is the shear force diagram and also bending moment diagram. So based on the bending moment and shear force diagram, then we are going to design our steel beam section. Okay, laterally restrained beam. So LTB. What is LTB? It means that the beam does not fail by lateral torsional buckling. So to provide the torsional buckling, so we have to put full lateral restraint on the beams, which is we need to provide cast in situ or precast concrete slab support directly on top of the flange of the beam, so that it will prevent the beam from rotating when we apply load. Or we can add steel plate floor welded or bolted to the flange of the beam, or timber floors and beam fixed to the flange by cleats, bolts or similar method. The idea is you need to put something on top of the beam so that it's not going to rotate. Okay, so this is an example of full lateral support. For example, this one, they have a composite beam, which is we have a slab on top of it and it bolted to the beam. Or intermittent lateral support, it means that we have provide at some distance a support on top of the beam so that it's not going to rotate. For laterally restrained beam, it can fail due to, so these are elements that we are going to look in the design. The first one is local buckling of flange and web due to the bending moment. Then you need to check the yielding of the beam due to the bending moment and also shear force. And also we have to check the web buckling of the beam due to shear force and the combined effect of shear force and bending moment, and also web bearing and web buckling due to concentrated load. Okay, so these are the failure that might be happen in beam design. Alright, for the first part of the beam design, so we are going to cover this part only, the first step and also the second step, which is the first one you have to determine what is the design shear force and also what is the design bending moment at critical point. And from the given moment, we are going to select our section if the size is not given. Right? Okay, so let's look into the step. Okay, the first step is you need to design shear force and bending moment. So you have to calculate what is the shear force and also the design bending moment, and we normally take the maximum value as our ultimate design load. Okay, so usually maximum shear force occurs at support and maximum bending moment will occur at the midspan or support. So this depends on the structure itself. For let's say you are designing a simply supported beam, then you are going to get your maximum shear force at the support and the maximum bending moment at the middle of the span. Okay, so in order for the design, the beam section that we are going to provide must be adequate when the design shear force that we calculate is less than design plastic shear resistant VPLRD. And also the design bending moment that we calculate must be less than design plastic moment resistant. Okay, it means here the design force should be less than the resistance. So then it means that our beam section that we are providing is adequate. Okay, so to calculate the design shear force and bending moment, so the first one that you have to do is to calculate what is the ultimate design load subjected to the beam. Since we have the permanent and variable action, so the equation is actually similar to the one that you have done during concrete design. So which is for ultimate design load is equals to 1.35 GK plus 1.5 QK. For our syllabus, we are going to design only for simply supported beam. So the design shear force and design bending moment is using this formula. VED is equals to uniformly distributed load times the length divided by 2. Or we can also write as F divided by 2, which is the F is equals to W times L. Okay, forces divided by 2. And for design bending moment, the MED value, we can take WL squared divided by 8. Or we also can write as FL divided by 8, which is F is the WL. Okay, so then you are going to get what is your design shear force and also design bending moment. Okay, so the next step is we are going to select a section. So let's say here we have one example. We have a simply supported beam of 8 meters length and is subjected to uniformly distributed load of 25 kilonewton meter. So we are going to propose what are the suitable size of the beam so that it can safely supporting the given load. So first of all, you need to calculate what is the MED value based on the loading that are given. Okay, from here we get our design bending moment is equals to 200 kilonewton meter. So next. Okay, a trial section should be chosen by obtaining the required plastic modulus. So this formula is actually taken from bending moment resistant, which is plastic moment resistant from the appendix. Okay, so we rearrange the formula so that since we don't have the moment, we don't have the size yet, so we need to choose one trial section based on the moment that we have here. M here is the MED value. So based on MED value, what are the minimum required WPL, which is plastic modulus of the steel section. And Fy is the yield strength of the steel based on the grade of steel that we are going to use. So what is the yield strength? So this one is given in design appendix page 2. Design appendix here is design appendix for steel section, okay? So you need to refer to design appendix based on your code 3. And the partial safety factors for gamma M is 1.0. It's always 1.0 unless you are using gamma M2, then it is 1.25. Okay, so based on these equations, we can calculate what is our plastic modulus value, the required plastic modulus to support the MED. Okay, so here is the clause in the appendix, page 1, which is stated here. What is the gamma M0, gamma M1, and gamma M2, and the value is here. Okay, so it mentioned here gamma M0 is equals to 1. Okay, and then for the yield strength, it's given in page 2. Okay, so you refer to table 3.1. This is the nominal value of yield strength and also ultimate tensile strength for hot roll structure steel. So for hot roll structure steel, okay, it is actually depending on the thickness of the element, and then you are going to get the value of Fy and Fu. Okay, so since given in the equation that the grade is S275, so we can take the Fy value equals to 275 and we calculate what is the required WPLY. So from here we get that this is our WPLY required. So we change the unit to centimeter cube because we are going to refer to the appendix, which is the given value of WPLY is in centimeter cube. Okay, so now you refer to your appendix. Your appendix, the last page, we have the appendix page or page B1 until B7 for I-beam. So we can choose the trial section based on the appendix given at the back of your steel beam design appendix. Okay, so please refer to B1 to B7, the section for beam. Okay, so given here is the dimension and also the axis for the I-beam. Okay, so we have the B is the length of the flange and TF is the thickness of flange. The H value is the height of the beam. D value is from here to here. And TW is the thickness of the web. Okay, and also the axis of the beam is the YY axis is the major axis that cut through the center of the beam, and the ZZ is the minor axis which is in line with the web of the beam. Okay, so from the previous calculation, we get the required WPLY is 72.73 centimeter cube. And the plastic modulus is WPL in Y direction, YY axis. So based on this appendix, we can choose the size of, okay, so from the appendix, you can refer to here. We have section designation, and then you have second moment of area, radius of gyration, and elastic modulus, plastic modulus. So we are going to look into plastic modulus in y-axis. So you need to choose the value that is greater than 72.73. So from here, from this page, I think this one is page B7 in the appendix. Okay, we can take here that the value of design section of 1277 times 76 times 13 is actually, we get here the value of plastic modulus is greater than the required value. So we can try this section to design the steel beam. So we can use this section to design the beam. Okay, and also at the appendix B6, so the same size of the beam, so you need to extract all the design data. So we are going to use this one, the size of the beam. So I think this one is in appendix B6 and this one is in appendix B7. Okay. Okay, so from B6, it gives you the dimension of the beam. So which is what is the weight of the beam per meter, the height of the beam, the width of the beam, thickness of web flange, the radius, the depth, the ratio, and so on. Okay, and the other one at B7, we have the properties of the beam, which is the second moment of area, radius of gyration, elastic modulus, and plastic modulus, and also here we have area of the section. Okay, all the properties is given in the appendix, so we just need to take out all the design data for that we can use to design the beam. And please take note on the unit here at the dimension part, all the unit is in millimeter. However, at the properties part, they are using centimeter. Okay, so you need to make sure when you are using any formulas that the unit that you use is similar. Okay, for another example, let's say we have the given size in the question. So we already have the size of the beam. We need to check whether the beam can support the loading or not. So for this one, this example, we have the same beam with the same loading. We need to check whether this beam size is adequate to support the loading. Okay, so the MED is similar, which is 200 kilonewton meter. Alright, so since we already have the size of the beam, so all you need to do is to extract all the design data. So please take note that normally for section designation, 152 is actually represent the height of the section and 89 is actually represent the width of the section. And 16 is actually the weight of the section. So from this table, these two tables, you need to extract the H value, B value, TW value, TF value, R and D value. And then you need to also have this value and this value. Okay, you extract all the information and then you are ready to design the section. Okay, so that's all for the first part of the beam design, which is you need to select which section that you are going to use for the design. We are going to continue for next topic, which is the second part of the beam design, which is you need to check the bending moment and the shear capacity of the section that we choose. Alright, thank you very much. See you next time.